Thank you. Let's get started. So, as many of you are likely aware, almost every programming language compiles to JavaScript these days. So here we have a list of implementations and compilers for Python that run in a web browser. And Python's not an isolated case. Essentially, you can pick your choice of programming language and find at least one, if not several, implementations targeting the browser. And all of these systems are providing you more options for programming for the web. We've also seen an increasing trend towards programming within the web browser itself. So there are dozens of online coding schools, all of which offer in-browser programming environments. And these are backed by venture capitalist funding, and many of them claim millions of users. So what does programming for the web in the web look like right now? One such website is Khan Academy. And Khan Academy is an education platform which offers a programming environment where you can write and run JavaScript programs in the browser itself. So here we see it's a little bit small, but I've written a simple loop program that just loops for, in this case, 100 trillion iterations. And after some amount of time, we see that Khan Academy prints an error to the user. And what it says is, your program's been running for too long. Maybe you made a mistake. Maybe you wanted to loop 100 trillion iterations, but Khan Academy won't let you. It's performing some form of infinite loop detection and saying your program can't run for too long in the browser context. But the matter gets even worse. So let's look at another environment. Here we can write and run OCaml programs in the browser using the BuckleScript compiler. And again, I'm going to write a simple program that just infinite loops. And this environment actually will evaluate your code as you're typing it. So once we call this infinite loop function, you'll see I can click around the web page, but the page is no longer responsive. I can press buttons, nothing happens, seems like I'm out of luck. Eventually the browser actually tells you, something is slowing down your browser. Do you want me to stop it for you? And this is not ideal. This is not good. So let's look at another environment. Here we have a programming environment for Dart, and Dart's a language specifically targeting the browser as an alternative to JavaScript. In this case, we have a Fibonacci program where when we press the run button, it runs in the browser as well. When we call it on Fibonacci 20, it terminates quickly, but if we change the input to Fibonacci of 200, we get the same behavior. The browser is now locked up, it's not responsive to user interaction, and again, the browser offers to kill the web page for us. So why is all this happening? This seems very bad. I'm going to claim this is not desirable behavior for any of these environments. And the root of the issue is that JavaScript executes in a single-threaded context within the browser's event-driven runtime model. And if you're familiar with modern web technologies, you might be thinking, what about web workers? What about WebAssembly? Do they help us in any way? They somehow sort of subvert the single-threadedness of the browser. Maybe we can just use them. And unfortunately, these technologies don't address the fundamental issue that these environments are facing. They don't provide built-in constructs for arbitrarily suspending and resuming computation, for instance. And furthermore, they lack direct access to DOM APIs. So here, we want to be able to use language-specific graphics libraries, such as Turtle Graphics for Python, and these are not natively supported when you're using web workers and WebAssembly. So we want a first-class solution to this in JavaScript itself. So let's take a closer look at what's happening in the browser's runtime. Here we have a hypothetical programming environment with a run button and even a stop button, which is what we really want. And it's small, but I've just written the mutually recursive implementation of odd and even functions, and I'm calling it on a fairly large input. So the program begins when the user presses the run button, and this adds a run event to the browser's event queue. The program begins executing and building its call stack at runtime. And eventually, the user presses the stop button. And again, this adds an event to the event queue, but the program is going to continue running for some amount of time. And in fact, the user can press the stop button as many times as they want to, adding as many events to the queue as they want, but the program is going to run potentially indefinitely. And the issue here is that the event queue is blocked processing the run event and can't process any of the stop events that the user is clicking on the button for. So the event queue processes events sequentially and each event to completion. so stop events can't be processed until run terminates. So there's a solution to this. What if we develop compilers which cooperate with the browser's runtime model and generate programs that work around the issues of its runtime? And like I said, there are dozens of compilers targeting JavaScript these days. Maybe they address the issue for us. But as we've seen, nearly all of these inherit the same limitations of the browser's runtime model. And there are a couple exceptions to this that actually do address the issue for specific languages that I'll talk about a little bit later. But most of these fail to solve the problem for us. And to that end, we've built a general solution to this. Stopify is a system which adds execution control to JavaScript. So using Stopify, we can take existing languages which compile to JavaScript and apply Stopify, compiling JavaScript to JavaScript itself, adding support for features such as stop button termination, single-step debugging, long-running computations, proper tail calls within the browser, arbitrarily deep stacks, blocking APIs, and more. And importantly, Stopify builds all these features what I call once and for all, meaning all of these languages which compile to JavaScript can leverage Stopify to gain these features in those languages as well when running in the browser. Stopify provides these features by implementing first-class continuations for JavaScript. And there are many ways that we could have implemented this. So you might be thinking, are we just doing continuation passing style? There's an alternative. Maybe we use JavaScript generators to provide continuations in some form that can provide similar features. And we implemented both of these strategies, but ultimately ruled them out because of performance concerns. So instead, Stopify actually implements 3 different strategies for capturing continuations in JavaScript. And essentially, each of these strategies are maintaining a copy of the program's runtime call stack off to the side. Stopify presents these 3 strategies in a unified framework, so when you compile with Stopify, you can simply pass a compiler flag and choose between them. And we'll see later that this is important because these strategies perform differently on different platforms. So having a parameterized instrumentation strategy lets us get the most performance out of Stopify as we can. So let's revisit our running example and see how Stopify helps address this issue for us. Again, we have mutually recursive odd and even functions, and the program begins when the user presses run. The program builds its call stack at runtime, and just as in the first example, the event queue is blocked on this run event. So when the user presses stop, an event's added to the queue, but it's not processed immediately. Stopify's instrumentation causes programs to periodically capture the current call stack off to the side, and this call stack represents the program's continuation. Once it has the continuation in hand, Stopify adds a resume event to the browser's event queue, telling the program, restore the captured continuation from where we suspended. With all of this information, Stopify then just terminates the program. By doing so, it frees up the event queue to process any events that have been queued. So here we see the user press the stop button, so we can simply throw away the continuation that Stopify has captured. If the user hadn't pressed the stop button, the resume event would be processed, which would just restore the continuation instead of stopping it. And we apply Stopify to many different programming languages, but let's look at one example. So we've taken a suite of Python benchmarks, compiled them to JavaScript using the third-party PyJS compiler, and then we've used Stopify to provide graceful termination, long-running computations, and blocking APIs to these programs. And we evaluated these benchmarks in Chrome, and unfortunately saw that performance is bad. So on a set of 10 benchmarks, we saw a median slowdown of 6.6 times slower than the uninstrumented version of the PyJS program. And the max slowdown was actually above 30 times slower. So this is not ideal. We want the features that Stopify provides, but we don't want to pay such a high cost for them. And this begs 2 questions. The first of which is, why is performance so bad? And can we do any better? We want these features, we don't want to pay the cost. And to answer the first question, let's go on a short tangent. And I want to consider the JavaScript program x+1. This is a simple program, about as small a program as you can have, but even this program can infinite loop in JavaScript. And that's because JavaScript, like many programming languages, implicitly converts overloaded operators such as plus to invoke toString or value of methods. And in JavaScript, we can dynamically redefine toString on objects to perform computation. So in this case, we redefine it to an infinite loop, and x+1 now diverges. So this seems bad. Stopify has to instrument programs to account for this type of behavior, which essentially means we have to make all of these implicit conversions explicit, adding more runtime overhead. But does Py.js generate code that actually uses these implicit conversions? If it doesn't, we can feed that information into Stopify and achieve more efficient instrumentation. So if we zoom out for a minute, we can think of JavaScript as this giant monstrosity of a language with lots of dynamic language features. And these features make performance hard to achieve for Stopify. But when we consider languages which compile to JavaScript, we observe that they target restricted sub-languages, which don't necessarily make use of all of the language features JavaScript offers. Of course, if JavaScript itself is your source language of choice, then Stopify has to instrument all of these features potentially. So in this case, Stopify will incur the highest runtime overhead. So JavaScript is actually the hardest language for Stopify to deal with in this case. But let's take a closer look at Python as our running example. And as noted before, I mentioned Py.js generates code that does not make use of implicit conversions. So we told Stopify not to account for them in its instrumentation. When we evaluate this strategy on the same set of Py.js benchmarks, we're able to reduce the median slowdown from 6.6x to just 1.7x slower. And 1.7x is still a cost to pay, but this gives you continuations for JavaScript and all the features you can build with that. So many of these benchmarks actually would lock up the browser page when running them uninstrumented, but with Stopify, we can run these programs and more in the web browser itself. So we didn't only evaluate Python in Chrome, we actually evaluated it across 5 different browser platforms: Chrome, Chromebooks, Microsoft Edge, Firefox, and Safari. And as I mentioned, we evaluate, well, in this case, 16 Python benchmarks gathered from the computer language benchmark game as well as some PyPy benchmarks. And you can read this CDF graph as saying the percent of benchmark trials on the y-axis executed with less than or equal to the slowdown on the x-axis. The median slowdowns are shown in the legend. So the median slowdown ranges from 1.7x in Chrome, or 1.4x actually in Chromebooks, to 3.8x slower in Edge. And the colors might be hard to read, but you might notice that Edge and Firefox don't perform as well as the other browsers on these benchmarks. And I wouldn't read that as indicative of the browsers themselves. Stopify was mostly developed against Chrome and Safari, and we feel with more engineering effort, we could improve the performance in Microsoft Edge and Firefox as well. So I mentioned we also applied Stopify to more languages, and there are 9 languages shown here. And there's way too much information, way too small to get into detail of these graphs, but I have a couple points that I want to note. And first, the slowdowns we saw with Stopify were comparable between Chromebooks and desktop Chrome. And this might be surprising because Chromebooks have very small cache sizes. So Stopify is not actually relying on the hardware that it's running on to achieve its performance. And second, the slowdowns that Stopify incurs are correlated with the sublanguages of JavaScript that compilers target. So languages that use less of the dynamic language features tended to have lower slowdowns. The other side of end-to-end performance is how responsive are these programs running in the browser. Some of the features Stopify provides require us to preempt execution at arbitrary points in the program. And this is made difficult because programs can execute in different, what we call types of phases. So you can imagine that a program might execute in one phase a small number of statements, each of which takes a long time to compute. So these might be built-in browser APIs, for instance. But in another phase, it executes a large number of statements, each of which runs very quickly. And these different types of phases require us to suspend at different frequencies to maintain responsiveness in the browser. So for preemption, again, we have several options for how we could implement this. We could suspend execution in instructions, or say in function calls. When we evaluated this, we observed, however, that there's large variation between the points at which Stopify suspends, meaning your browser might still hang for a period of time. Alternatively, we could use JavaScript's date.now API to query how much time has passed since the last time Stopify suspended. But when we evaluated this strategy, we noticed the date.now API introduces a high runtime overhead. So we've implemented a third strategy, which approximates the number of instructions over a window of time. And using this strategy, we're able to reduce the runtime overhead of our preemption and achieve a preemption strategy that adapts to phase changes in execution quickly. So it maintains the target suspension latency. And we evaluated each of these three strategies on the same set of PyJS benchmarks as before, targeting a latency of suspending every 100 milliseconds. And as expected, counting down to suspend every in instructions had both low accuracy and low precision of hitting the target. The date.now API had high accuracy and high precision, whereas our approximation had high accuracy and achieved the target latency with reasonable variance. And again, just to point out, the date.now API is slower. So the median slowdown for date.now API was 1.4 times slower than our approximation method. So far, we've considered how Stopify performs against itself. That is to say, how can we tweak aspects of Stopify to achieve better performance for it? But we also care about how Stopify performs against the state of the art. And there are a few systems out there that provide similar features, but for single programming languages for which they were designed to target. And Sculpt is one such system. Sculpt is an implementation of Python in JavaScript, and it instruments programs with this periodic suspension mechanism. And Sculpt is used by many companies and in academic institutions such as Code Academy, CodeHS, REPL.IT, and at Rice University, and there are millions of users who interact with Sculpt. So we evaluated how Sculpt performs relative to how PyJS plus Stopify performs to provide the same set of features. And the y-axis is hard to read here, but on all but one of the benchmarks, Sculpt was actually over 2 times slower than PyJS plus Stopify. And there are some caveats to this, but Sculpt also has some soundness issues, meaning we couldn't evaluate on the same set of benchmarks because Sculpt actually crashed the web page when trying to run them. The state of the art in academic research is the Pirate programming language. And this was developed by my collaborators and co-authors. And Pirate is a mostly functional language that's specifically designed to offer a native feeling programming environment in the web browser. It does much more than just instrumenting programs with a suspension mechanism. It also offers an in-browser REPL, as well as simulating blocking APIs, and the compiler itself runs in the browser. And we want to evaluate against it as well. But to do so, we need to do a little extra work. So Pirate generates code that's already instrumented with a suspension mechanism. So you can think of its compiler toolchain as taking a source Pirate program, feeding it to the compiler, and just generating a JavaScript program already instrumented. We re-engineered the Pirate compiler to use Stopify for instrumentation instead of its hand-implemented mechanisms. And in doing this process, we removed lots of fragile instrumentation logic, fixing lots of bugs in the process. And this also introduces a new compiler target for Pirate, which just bypasses any instrumentation, meaning we can run Pirate programs with better performance in certain environments. And this new Pirate compiler using Stopify is able to bootstrap itself. So we are now able to evaluate Pirate against our new Pirate plus Stopify compiler. And here we took 21 benchmarks that the Pirate developers maintain in their compiler repository and evaluated them again. So you can see in the median, in the legend, the median slowdowns range from 1.1x to 3.7x slower than the mainline Pirate compiler. So we're often able to perform comparably. There is, however, at the top of the graph, a long tail where mainline Pirate outperforms us. And most of these benchmarks fall into programs that use unbounded stacks. And this means that capturing and restoring continuations takes more and more time as the continuations grow. And here, we think that with more engineering effort, Stopify can improve its performance on unbounded stacks as well. So today, you can go to our website. It's at stopify.org. You can choose between a number of different programming languages, run them, pause them, single step through them, stop them, all running code within the web browser itself. We're in talks with an education technology company about incorporating Stopify into one of their programming environment products, and we're continuing our efforts to release Stopify in Pirate's production environment. Thank you.
Hey, thanks for a great talk. I was wondering about the remaining slowdown that you get from Stopify after you've made your efficiency savings, and I guess that comes from all the yield instructions that you instrument your code with. And I was wondering if there's a trade-off between, could you insert fewer yield instructions, so you only yield once every second, 5 seconds or something, and get much less slowdown? Is that right?
Certainly, yes. For all of our benchmarks, we were configured to suspend every 100 milliseconds, maintaining the browser's responsiveness. Removing that or lifting it to about 1 second or so. On some benchmarks, it was up to like 2 or 3 times difference in terms of end-to-end runtime performance. There's also differences in how many suspensions we insert into the program. For instance, if you have nested loops, we could only suspend in the outer loop, and that would further increase performance, but we didn't evaluate those different strategies. Thanks.
Most of your examples seem to be educational environments for general purpose programming in browsers. If we look beyond that segment, will we still find enough cases with computationally intensive client-side code that we could tell the difference between your different implementation strategies and optimizations?
Yes, I think there's definitely examples out there. For instance, I think fairly recently, Facebook re-implemented their React async rendering to incrementally render changes to DOM events. Okay. I think you could perform this type of asynchronous rewriting using Stopify instead and not having to rewrite the code. We didn't implement a comparable system to evaluate against, but I think there's also areas where we could apply Stopify. For instance, people are starting to implement machine learning algorithms and things of that nature in JavaScript, where you have potentially long-running programs where it would be interesting to see how Stopify performs against their hand-implemented strategies. So,
thanks.
Yeah. Thanks.
Hello, and thank you for the talk. So, in your instrumentation, you are encoding assumptions about the subset of JavaScript targeted by a specific compiler. Mm-hmm. And my question is about how stable are those assumptions, and what happens if a compiler is updated so as to violate those assumptions?
Right. So for some of these languages, we chose those sublanguages by observing the output of the compilers. So we looked at the programs that they generated and noticed they didn't use language features. For some languages, we actually looked at the source code of compilers and verified that they didn't generate code that used them as well. Right now, if a program uses those language features that we don't account for, Stopify's suspension mechanism might not capture the full call stack. So it would still be able to instrument the code, and it might run some of the time, but there might be non-deterministic bugs depending on when the program suspends. But I think there's things we could do to detect that the program is using those features.
Okay. So basically what I'm hearing is that if the compiler if compiler gets updated so as to change its output code in a way that breaks your assumptions, then you fail silently.
Yes, yeah, I think there's things, though, we want to encourage people not to use these language features so that we can achieve better performance. So that's part of the message. So.
Do you think it would be beneficial to build the preemption mechanism into the browser so that the JavaScript app only gets interrupted when there is a high priority event pending?
Yeah, I think it might be difficult to add that type of instruction to JavaScript.
No, I don't think about JavaScript. I think more like a high priority input event gets scheduled. It tells the JavaScript engine like there is something pending and forces it to go to a save point like the garbage collection save point, where you can evaluate that, oh, there's something going on, and then you start your protocol and take a snapshot of the stack. With that, you wouldn't impact any benchmarks because they wouldn't do that, and you would only do it when needed.
Yeah, I think that could be a solution to get a lot of the features Stopify provides without the instrumentation overhead. I don't know what that process looks like for adding that type of feature to the browser, but I think there's also room for, we're trying to suggest this type of language feature for environments such as WebAssembly, where they are still at the point where they can incorporate that type of language feature without disrupting a lot of the current ecosystem. So, thanks.
More questions? No? Okay, let's thank Sam again.